grade 10s and welcome to our second lesson on analytical geometry. Now you'll remember that last week we covered the straight line and we talked about the gradient of the line and the y-intercept. You've been doing a lot of work on linear functions and now the straight line within analytical geometry. So I hope you realize how important it is that you get it right now, rather than waiting until you're in grade 11 or grade 12. This is where you should master those skills. But analytical geometry is not just working with a straight line on the Cartesian plane. It's also working with some other formulas. Two of those formulas are the midpoint formula and the distance formula. And those are the two formulas we're going to cover today. But before we do that, we're going to revise a little bit of terminology. And the terminology is stuff that we went through last week. I would like to give you 2 minutes to go through each one of these words and just write down what they mean. So write down what gradient is. Let's put it in pink. Write down what the y-intercept is, x-intercept, what collinear, parallel lines, and perpendicular lines. You have 2 minutes starting now. Okay, so grade 10s, how did those definitions go? I hope they are all things that you remember. Maybe you struggled a little bit with the word collinear, but we'll go through it all now. So, the first word you had to define was gradient, and as we know, that's the steepness or the slope of the line. To find the gradient, we use this formula. Now, the great thing about this formula is that it is on the formula sheet, so you don't have to remember it. But what you do need to remember is that you're going to work with two different points. You've got your first point, which is called xy, or something. And your second point also has an xy coordinate. And the problem is they both look exactly the same at this point. So, as mathematicians, we do this fancy thing. We say we're going to call this point 1, which means that this is x1 and this is y1. And we're going to call this point 2, which means this is x2 and y2. So that x2 value gets substituted over there, and the x1 value second. It's really important that you realize that if the second point, the coordinate, x-coordinate of the second point goes first, the y-coordinate of the second point should also go first. Okay, let's move on and see what the y-intercept is. And obviously, that is the point at which the line cuts the y-axis. So let's just label it y-intercept, and we know at that point x is equals to 0, but y will be equal to something else. Now the x-intercept is the point at which the line cuts the x-axis, and at that point y is equals to 0, but x, we're not sure what it's going to be. You also know that the y-intercept in the formula y equals mx plus c is going to be your c value. Let's move down. Now collinear are points on the same straight line. There are different ways to calculate this. You can check that the gradient between that point and that point, let's call it m1, is the same as the gradient between that point and that point, m2. So m1 equals m2. Or you could check if the distance between point 1 and 2 plus the distance between point 2 and 3 is the same as the whole distance, let's call it d3. In other words, does d1 plus d2 equal the distance of d3? So that's how you prove that points are collinear. Now we also have parallel lines. They remain the same distance apart at any point, so they never ever cross each other. And parallel lines have gradients that are the same. Perpendicular lines intersect at a 90-degree angle. Let's just label those, which means that if we multiply the gradients together, what value should we get? -1. And so that means that if we had a gradient of half for the first line, our second gradient should be -2. Why? Because a half times -2 gives us a -1. Those two numbers are the negative inverse of each other, negative inverse. So when you want to look clever later today, you just tell people that you know what the negative inverse of half is. Okay, but we're going to move on to the key concepts for midpoint. And maybe before we look at the slide, let's talk about midpoint and what the word actually means. So, if I have a point over here and I have one over here, now somewhere along this line there is going to be a middle point. And we call that middle point the midpoint. Why do we abbreviate it? Because mathematicians are lazy, we know that. So if we were to think about it logically, how would we find the middle of those 2 points? What if it was on a normal number line and I wanted to find the middle of between the point 2 and 6? What would be the middle point? You probably said 4. And that's good, because it means you're using your intuitive understanding. Now 4 is in the middle of 2 and 6. Now, finding the midpoint is exactly the same operation, except instead of just being on one number line, we're working on the Cartesian plane, which of course has those 2 lines like this. So we need to find the middle point of the x coordinates, so that's going across, find it. And we need to find the middle point of the y coordinates. So it's 2 different calculations in the same package. Why do we write it in the same package? Mathematicians are lazy. So let's take a look at the formula. Now the formula you do get on the formula sheet. So let's draw a smiley face over there because it is pretty exciting. Let's say I have a coordinate of 2 and then I have another one of 6, and let's make y equal to 7 and -3. Now you'll notice I've used different colors because I want to emphasize the 2 different calculations that are happening. We've got the first one where x1 plus x 2 divided by 2 will equal, let's name this point 1 and this point 2. So that's going to be 2, because there's my x1, plus 6, my x2, divided by 2. What value does that give me? Gives me a value of 4. What did we guess it would be? We did guess it was going to be 4, so that's quite good. And let's do the y values now. So the y calculation is y1 plus y2 over 2. Our y1 value is 7, and our y2 value is minus 3. So I'm just going to put it in brackets. Not really because I need it, but because it just helps me. And that means I've got 4 over 2, which gives me a final answer of 2. Now, have I finished the calculation? Not really. If I needed to find the midpoint, I should write it as an answer of the midpoint. So the midpoint between these 2 points is actually 4 and 2. Yes, I could have got that by just looking at it and going, well, the midpoint of 2 and 6 is going to be 4, and the midpoint of 7 and 3, negative 3, is going to be 2. But the calculation just makes me feel confident, and a lot of maths is just making you feel good about yourself. So remember, there are 2 different calculations. You're calculating the x value and you're calculating the y value, and you must put it in coordinate form. Now the next thing we're going to look at is the distance formula. The distance formula is based on Pythagoras. And you'll remember Pythagoras is all about right-angled triangles, and we use it in quite a lot. Ooh, I almost made a right-angled triangle there. And with a right-angled triangle, the sum of the 2 squared sides equals the hypotenuse squared. So in our formula, we're going to have a couple of squareds and we're going to have a square root. Why do you think we have a square root? Well, it's because we don't actually want the length of the hypotenuse squared. We just want the length of the hypotenuse. So we need to square everything. Let's take a look at the slide. Okay, now to find the distance between the 2 points, we use the formula d is equals to x1 minus x2 squared and y1 plus y1 minus y2 squared, and then that's square rooted. Now let's draw this as a calculation. I have a coordinate over here. I don't know why I did that as a 2. Maybe I'm just counting as in my head. But x1 and y1 is over there. Now I have a coordinate over here, x2 and y2. I want to find out the distance of that line, but as it currently is, it's not going to be easy. So the theory behind it is we make this imaginary triangle, and we say that this value over here, or this position, is the position x1. And this position over here is the position x2. What is the distance between those 2 points? Well, it's going to be x2 minus x1. Okay, and we say that that position over there is y2, and that position over there is y1, because look, it's in line with y1. So what is the difference or the distance between those 2? Well, it is y2 minus y1. So if I treated those as the lengths, how would I find the length of the hypotenuse? I would use Pythagoras. And Pythag says, let's just write Pythag, the hypotenuse squared is equals to the one squared and plus the other squared, which means we have got our distance squared is equals to x2 minus x1 squared plus y2 minus y1 squared. Do I want the distance squared? No, I don't. I want it just to be a normal distance. How do I get rid of the square root? Well, I get rid of the squared by square rooting both sides. Now, I'm sure you've noticed that in the original formula, it started with x1 minus x2 and then y1 minus y2. The truth is, you can either put the x2 and y2 in the beginning, or you can put the x1 and the y1 in the beginning as long as the same coordinates are in the same points. So grade 10s, when we come back, we're going to go through some questions. And I want you to be on top form and be ready to try and answer them yourselves. We're going to have a lot of fun. I'll see you after you've had a bit of a break. Okay, grade 10s, you feeling refreshed and ready to go? We're going to start now with a question that I've purposely phrased so that it gives you a lot of room to try and explore what you need to do. In other words, I want you to think. Okay, now you must remember in analytical geometry, you need to still know all of your characteristics of different triangles. So scalene, obtuse, acute, right angle, isosceles, equilateral. You need to know all of those. And you also need to know all of your characteristics of your quadrilaterals. So squares all have the same length sides and their angles are right angles. And things like that. Those are essential to answer these types of questions. Let's look at the first one. A triangle with the vertices, and vertices is another word for corners, except it's the real word. The vertices A, -1 and 7, B, 8 and 4, and C, 5 and -5 is given. Now you'll notice there's no picture, which means you need to try and think of it. What will it look like? And draw it yourself. Do you really need to draw it? Not really, so that's quite good news. We can just use our brains. Okay, and our calculations. Determine the characteristics of the triangle. Show all calculations. Now, what does characteristics mean? Is it isosceles? Is it equilateral? Is it scalene? Is it right angle? Is it obtuse? Is it acute? Okay, grade 10s, I'm going to give you 3 minutes to try this by yourselves. Good luck and enjoy it. Think. Okay, grade 10s, how do you think you did? Were you able to use the distance formula to help you? Was there anything else that you could use to help you? I'm going to show you how I do it, and then you can compare your calculations to mine. Let's see. Okay, so we have 3 corners. I'm not going to draw it to scale or anything, but it does help me to just picture some kind of triangle. I have A, which has a coordinate of -1 and 7. I have B, which has a coordinate of 8 and 4. And I have C, which has a coordinate of 5 and -5. It's definitely not to scale. There's nothing to scale about this, but it'll just help me. So the first thing I'm going to compare is the distance of each line. And I'll start off with the distance of AB. Do you see how I named the distance calculation? It's very important that you do that. Okay, our distance formula is x1 minus x2 squared plus y1 minus y2 squared. So let's choose which coordinate will be my 1 and my 2. I'm going to make A1 and B2. So that means my x1 coordinate is -1 and my x2 coordinate is 8. I'm going to square it. And then my y1 coordinate is 7 and my y2 coordinate is 4. And let's square it. Okay, at this point you should be able to use your calculator to get the answer. And let's do that, because why not? We've got the tool, let's use it. And you can type it in exactly as you see it. Although, if you can do it in your, oh, I missed out a 1 there. Let's just go back. If you can do it in your head, it does save time, but you must just be confident that you are checking your work properly as you go along. Otherwise, you can run into problems. So we're typing in all of the numbers and look at what we get, 3 square root 10. Now one of the tricks with this section is to leave things in simplified surd form for as long as possible. So write down the simplified surd and then let's change it to be 9.48. So let's round it up to 9.5. So that's the distance of AB. Now let's do the distance of BC. Why am I finding all of the distances? Because I want to compare them to see if they are isosceles, equilateral, or scalene. Now let's change the labeling, because now we're doing BC. I'm going to call B number 1 and C number 2, and that will just help me with using my distance formula. So it's going to be the square root of 8 minus 5 squared plus 4 minus -5 squared. What tool do we have that can do this calculation for us? Yes, we have our calculator. So let's just clear all of that, put the square root in, and we'll put the 8 minus 5 and square it, plus, and let's put the 4 minus, and I'm going to put a bracket in for the -5, and remember to close both of them. Put the squared in, and let's see. Whoa! Do you see that that's the same as the other answer? So that means that our triangle is either going to be isosceles or equilateral. At this stage, it's isosceles because we've got 2 sides that have the same length. But let's see if the third side has the same length. And in order to do that, we're just going to give ourselves more space, and we're going to calculate the distance of AC, which means I'm going to go up here and just relabel things again for myself. And once again, this is just a way to make sure that I keep my x's and my y's from the same coordinates in a good place. So it's going to be -1 minus 5. Let's change to blue just because that's what we've been working in. So -1 minus 5 squared plus, and then we're going to have 7 minus minus 5. 7 minus minus 5, and we squared that. And now we have this excellent thing called a calculator to help us out. And let's put the square root, and we have -1 minus 5, and we're going to square it. And then we've got plus, in brackets 7 minus, open up brackets again, minus 5, and close off both of the brackets, square it. We've got an answer of 6 square root 5. So it is not an equilateral triangle. It is an isosceles triangle. But we've only found out one thing about it, and that's about the lengths of the sides. Did you notice that all of these top characteristics were all about the lengths of the sides? What about the angles? There are two different ways we could determine if the triangle had a right angle or not. We could either use Pythagoras, which of course is the hypotenuse is equals to the, hypotenuse squared is equals to the sum of the other two sides squared. Or we could calculate the gradients between them. Now, because I have already calculated the distance of all three lines, I am going to use Pythagoras. And I'm going to suggest, actually let me get my calculator out and put this in simplified surd form. 13.4, we'll call it. Now we know that the hypotenuse is always the longest side. So let's try adding these other two numbers together, the square of these other two numbers, that one and that one, and see if we get the squared of that. In other words, what is 3 square root 10 squared plus 3 square root 10 squared equal to? Well, let's use our calculator because we can. And it's going to be 3 square, 23, where did that come from? 3 square root 10, delete 10, and then we'll move out of the square root, close the brackets, square it, and we're going to add 3 square root 10 and close the brackets and square it. Okay, and that is equals to 180. 180. Now let's see what 6, put it in brackets, 6 square root 5 is equals to when it has been squared. I'm losing my place all over the place. And close that. And 180. Isn't that fantastic news? It is a right angle triangle. How do I know that? Because the 6 square root 5 squared is equals to 180. Therefore, not 180 degrees. Therefore, the triangle ABC is isosceles and right angled. Beautiful work. I hope you got that. Remember, the marker cannot read your mind. You must write down what your conclusion is. Okay, before we go on to the break, I want to introduce the next question so that you can start thinking about it. We have a diagram of a quadrilateral, and it's got all sorts of points on it. And it says, consider the diagram and answer the questions, show all calculations. Do the diagonals bisect each other? Okay, remember the diagonals are the lines between the opposite corners or the opposite vertices. So do they bisect each other? You must show your calculations. Okay, grade 10s, it's time to have another break. Think about this question while you're having the break, and remember the diagrams are not necessarily drawn to scale. So use your calculations. We'll see you just now. Okay, grade 10s, you feeling refreshed? Did you have a little talk about what does it mean to bisect? And how would that affect the diagonals? How would you calculate if the diagonals have bisected each other? Well, you can make it really complicated. You can make it really, really complicated for yourself. But because this is analytical geometry, we have some formulas that can help us to figure out whether the lines have been bisected. Remember that bisected means to be cut in half. So that means that this diagonal is going to cut that diagonal right through the center, but it is also being cut right through the center. And even though our diagram isn't drawn to scale, we can still see that no, they're probably not going to bisect each other. Now, the easiest way to tackle this problem is to find the midpoint of both of the diagonals. And if the midpoints are the same, it means that the diagonals are cutting each other at their individual midpoints. So let's find the midpoints of both of the diagonals. Now I'm going to start with the midpoint of AD. And I'm going to use a big M to indicate that I'm doing midpoint and name it AD. Now you'll remember that the midpoint formula is x1 plus x2 divided by 2, and that's your first calculation. Put the semicolon in to indicate that we have a separate calculation of y1 plus y2 over 2. So second calculation. In AD, so let's set up the two calculations. I am going to name I'm going to do AC apparently. I'm doing A as 1 and C as 2. Okay, so the midpoint of AC, both are going to be divided by 2. What is the x-coordinate of A? Because that's x1. That's 2. And the x-coordinate of C, which is x2, is minus 5. So I am going to say 2 plus minus 5. 2 plus minus 5. And then my y-coordinate, y1, is 5. And my my y2 is negative 2. So that's going to be 5 plus minus 2. Do we need our calculators? No, not really. This is pretty easy stuff. It's going to be negative 3 over 2, which is of course negative 1.5. And this is going to be 3 over 2, which is 1.5. I could change it if I wanted to negative 1.5 and 1.5, but it doesn't really help. So why do extra work if we don't have to? Okay, grade 10s, you'll remember that I said that if the midpoints of both diagonals were the same point on the Cartesian plane, that would mean that the two diagonals bisected each other. So now we're going to find the midpoint of the other diagonal, and then we'll see if they are the same point. Okay, so we've done AC, we now need to do BD. So let's write that down, give ourselves a little more space, and the midpoint, once again, capital M, so we don't get confused between gradient and midpoint. Midpoint calculation is set up like that. Let's check. Now just going to erase those 1s and 2s. I'll make B 0.1 and D 0.2, which means my x-coordinate is -3 and 4. So that's going to be -3 plus 4. And my y-coordinates are going to be 3 and then -4. So 3 plus -4. Once again, we don't really need a calculator. You can use it if you want, but remember, you've got 2 individual calculations, so do them separately. -3 plus 4 is -1 over 2. And 3 plus -4 is going to be -1 over 2. Are they the same? No, they are not, which means, therefore, the diagonals do not bisect each other. And I'm going off screen, but you get the idea. It's really important that you explain yourself. No one can read your mind, especially if you're not there to explain, to have your mind read. I mean, more than likely, your teacher's not going to mark your work at school while you're there staring into their eyes. Nope, they're going to mark it at home or during break or something like that. So they can't ask you, what did you mean? Write it down. Rather write too much than too little. But also be careful of your time management. Now the next question is an extension of this question. Let's take a look. Once again, we've got the same diagram. And we know that the diagonals don't bisect each other. Now we want to know what sort of quadrilateral is ABCD. Now you need to show all your calculations with doing this. So what are the types of quadrilaterals? We have a square, we have a rhombus, we have a parallelogram, palm, we have a rectangle, and a trapezium, and we have a, what's the other one? A kite. Did I get them all? I think so. I'm pretty sure I got them all. Okay, so I'm going to give you 1 minute to try and figure out which one of these quadrilaterals this shape is. On your marks, get set, go. Did you enjoy having your brain exercise there a little? What I really like about this question is it forces you to consider all of the properties of quadrilaterals and to try and eliminate things early. If you had started by trying to calculate the distance of each length of line, you'd be here forever. I mean, writing out the calculations alone would take you a good 4 minutes. And then on top of that, you would then have to compare them. And then, if all sides were equal, it could possibly be a square or a rhombus. But if 2 opposite sides are equal, then it could possibly be all sorts of other things. It really would be long and complicated unless we eliminated some of the things. Now, our first question was a bit of a clue. You were asked if the diagonals bisected each other. Now we know from Euclidean geometry that the quadrilaterals that have diagonals that bisect each other are squares, rhombuses, rectangles, and parallelograms. So because we know already that these diagonals don't bisect each other, we know that those 4 quadrilaterals are not possible answers. So let's just cross them off quickly. Why? Because that makes us feel not so intimidated. And that means the quadrilateral could either be a trapezium or a kite. Now, the one defining characteristic about a trapezium, let's do that, is that 2 of the sides are parallel. Oh, I did a terrible job there. 2 of the sides are parallel to each other. That's the only thing that is interesting about a trapezium. And I know that this is not to scale, but I'm thinking it's highly unlikely that that line is parallel to that one. And it's also highly unlikely that that line is parallel to that one. So I'm going to leave that as a second choice. And I'm going to start by trying to prove it's a kite. Now, you'll remember that a kite looks like a kite. It's got a short diagonal and a long diagonal. That side is equals to that side. And what else do we know about it? Well, that length is equals to that length, and this length is equals to this length. So we're going to start by finding the lengths of all of the sides. Well, and we're also going to spell it correctly. There's the N. We're going to find the lengths of all of the sides. And let's do this quickly because we're running out of time. D of AB is equals to square root of blah, blah, blah squared plus blah, blah, blah squared. We're minusing them. Let's see. AB is 2, negative 3. And then we've got 5 and 3. 5 and 3. Now it is faster for me to do this without the calculator, so I'm going to do it that way. I've got 5 squared plus 2 squared, which of course is 25 plus 4, and I'm just going to leave it for the moment at square root of 29. And let's do the distance of BC and see what that is. Set up my formula. Yes, these are all my tricks to get it done faster. Set it all up, then I only have to fill in the numbers. It's going to be negative 3 and negative 5, negative 3 and negative 5, and then the other coordinates are 3 and negative 2. So 3 and negative 2. Close that bracket. Yes, you can use your calculator. It's fine to do that. This, however, is still easier for me to do it this way. I'm seeing something exciting happen here. Look at that. That's exciting. Good stuff. Which means we're going to get an answer of square root 29. So now we know that the distance of AB is equals to the distance of BC. So we're on track for a kite. But have we proved it yet? Not proved yet. We still need to do the other set, but we're on the right track. So the distance of CD. Set up the calculation. We have the squared, and let's do that, and squared, put the minuses in, and let's go up. CD, negative 5 and 4, negative 5 and 4, and then we have negative 2 and negative 4, negative 2, negative 4. And that's going to give us negative 9 squared plus, and that's 2 squared, which is of course 81 plus 4, so it's a square root of 85. Square root of 85. The last distance I need to calculate is the distance of DA or AD. and we're going to set it up and put the minus in, and I'm going to scroll up quickly and grab the values 2 and 4, 2 and 4, and the values are 5 and negative 4, 5 and negative 4, which means we now have negative 2 squared plus 9 squared. And that, of course, makes me very happy because that's going to be the square root of 4. No, Helen, let's make a mess. 4 plus 81, which is the square root of 85, which means that the distance of DA is equals to the distance of CD, and therefore ABCD is a kite. Okay, grade 10s, with very little time left, so I just want to encourage you, this is a section you can get full marks for in any exam or test. Practice, practice, practice. I'll see you again next week. Goodbye.